Good afternoon, everyone. I'm a PhD candidate in NAM. My topic is prototype of a laser guide star wavefront sensor for the ELT. Um, Due to the large aperture of the ELT and the side laser launch configuration, effects like laser guide star spot elongation become silvery. Um, this introduces the inhomogeneity across the pupil and creates bias in the measurements. In order to handle such spot elongation and the associated effects, the motivation of the object is to develop a prototype to experimentally validate a full-scale version of a laser guide star wavefront sensor for the ELT. The prototype consists of elongated laser guide star source, turbulence simulator, ELT M4 simulator, microlens array, and a wavefront sensor camera. Now we have configured the point source whose wavelength is to simulate the sodium laser guide star, and the microlens array, which is 84 by 84 sculptures, and the wavefront sensor camera is 1600 by 1100 pixels. Um, at first, the camera measurements have been done because of the pixel construction. The incoming light at a different angle will cause how much protodiodes integral. This is so-called angle of acceptance. Um, Here we project a collimated beam in a large area on the detect plane and rotate the camera from minus 25 degree to 25 degree to test the relative intensity of the pixels. The camera is configured into first position and let it rotate along the x of each camera position. Here we acquire the angle of acceptance. The plot shows the angle of acceptance is symmetric with the beam angle, and it has obvious differences at a different camera position. This result follow our expectation well. And another camera measurement is spot center of gravity. The pixel size of the camera is 9 micrometer, and we acquire the spot is 1.1 pixels. We also rotate the camera from minus 25 degree to 25 degree, and at the same time let it move within 3 pixels at each angle. The center of gravity can be taken as a function of spot lateral displacement, detector rotation, and spot size. In generally outline, the center of gravity can be linear fitted, as this plot shown. If we consider the slope, the linearity is independent of the angle. If we remove the linear fit part to calculate the residues of the center of gravity, we can acquire the centroid variations. This variation is decided by the spot size and its shape, not by the detector. Because if the spot becomes smaller, its image will be undersamped, and the centroid variation, the amplitude of the centroid variation will become larger. Here we can see the error bar is a measurement, and the blue line is a fit curve, and the red line is a theoretic simulation. The fit curve and the simulation have a good corresponding. This verify the camera has good stability. And the next measurement is the micro lens array. We aid the optical relay and to aid the micro lens array to get the image. We get a preliminary result. We acquire 13 pixels per structure, and to get the spot is 1.5 pixels, and it has a good image of the micro lens array image. And the conclusion, we have made the noise analysis and angle of acceptance measurement and spot center of gravity measurement of the wavefront sensor, and to aid the optical relay and the micro lens array to get a very good cosmetic image. And these measurements done so far are fully compatible with the Harmony LTL specification. And the next step, we will aim at the elongated source and to integrate the prototype fully and to test it. And at last, to validate the wavefront sensor model. Okay, thank you very much.
Thank you very much, Zibo. So if there are any questions, please do not hesitate, don't be shy. I don't want to ask any question. We are working all together. We are working together every day. So no question at all. Okay, so let's. Thank you very much again, Zibo. Nice talk, and we're gonna move to the last speaker of the day. Yeah, Sylvain Auberti.
Yes.
From ISO, and Sylvain will talk about the FANTIA IR low order sensing and pushing the limit magnitude of the AOF in the LTO mode.